Okay, folks, I should suggest you fasten your seatbelts because we want to do a lecture on curve sketching. So basically, all the things we have learned in chapter 3, we want to put them all together and do a complete A to Z kind of curve sketching exercise. In order to draw the sketch of any function, there's 8 steps that we have to do. Step 1, domain analysis. Number 2, intercept analysis. Number 3, asymptote analysis. Number 4, intervals of increase decrease has to be determined. Number 5, local maximum minimum points need to be found. Number 6 is a concavity analysis where you find the intervals of concave up, concave down. And number 7 is inflection points if they do exist. And finally, step 8, the last step, is putting everything all together, and all the information that we have derived for a function, we're going to put them together and sketch the curve. And I have the intention of doing this whole thing, believe it or not. So I start with domain analysis for this quartic function. Domain of all polynomial functions is the set of real numbers. Therefore, the domain of this function is going to be the set of real numbers. So that was very easy. But if it was a rational function, perhaps I had to deduct the roots of the denominator from the domain of the function clearly. Intercept analysis. So I'm going to quickly set x equal to 0 to find the y-intercept. So if you do that, you are going to end up with 0 minus 0, which is 0. So the y-intercept is 0. And I'm going to set the y equal to 0 to find the x-intercept. And when I'm doing that, I end up with x cubed times x minus 2 equals 0. That's an equation I need to solve. One of the roots is x equals 0, and the other is x equals 2, clearly. I'm not showing all the steps, but it's easy. You know how to do it. So basically, I found 2 x-intercepts, and I found 1 y-intercept. So at this moment, I know that my graph, is going to pass through the origin for sure. My graph is going to pass through the point x equals 2, and the y-intercept would be at the origin as well. So this much information I have for now. So I continue with the asymptote analysis. Call me lucky. I don't have any asymptotes because this is not a rational function. So I'm going to say no asymptotes of any kind, actually. So I move on to step 4. If it was not a rational function, then I had to obviously do this step 4. It is part of the template of curve sketching. Intervals of increase decrease, well, here is where calculus kicks in. We need to take the derivative of the function. So y prime would be 4x cubed minus 6x squared. So that's the first derivative. And I'm going to need the second derivative so quickly, I'm going to find it anyway. 12x squared minus 12x. And then I'm going to go after the critical numbers, obviously. So I set y prime equal to 0, 4x cubed minus 6x squared equals 0. That gives me 2x squared, and that is 2x minus 3, if I'm not mistaken. Let me see, 4x cubed minus 6x squared, that's correct. So we will end up with x equals 0 and x equals 3 over 2. So these two numbers I found are critical numbers of the function f of x. Okay, critical numbers. Now, I'm going to construct my chart. You remember first derivative test, you have practiced enough, I assume. So I'm going to construct the chart. Where should I do that? Probably at this top I'm going to do it. So x, a negative infinity, all the way to positive infinity. This is the first derivative chart. I had two factors. 2x squared was one of them. The other one was 2x minus 3, right? And the product was nothing but y prime. Okay, and then we're making a judgment about y. So quickly, I construct the rows of my chart. The values I'm going to include 0 for sure and 3 over 2 for sure. And perhaps it's not a bad idea to include roots of the second derivative, which we're going to be finding shortly. So for now, let it be. So it's going to be like this and like that. 2x squared you know that it's always positive, right? Because it's because of the exponent of 2. So that's plus all the time. It's always plus. But then it's 0 at 0. 2x minus 3 is 0 here. And then it's positive to the right, negative to the left, always. The product of them is the sign of y prime, which is negative, 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 positive. All right. And we can say that the function is decreasing, decreasing, again decreasing, and then increasing. And it is y prime is 0 at 2 points. Okay, so this is a very interesting exercise. Y prime is 0 at 0, but it didn't change its sign. So it means that it's not a local minimum point. But if you look at x equals 3 over 2, y prime is 0, but it did change its sign this time from negative to positive, meaning that the graph was decreasing before, increasing after. So right away, I can announce this is actually a local minimum point right away. But I cannot say that for this other point because y prime did not change its sign clearly. But y prime is 0, meaning that the tangent line is horizontal. So if y prime is 0 and it didn't change its sign, it means that that point is an inflection point because the graph was decreasing before and it was decreasing after, right? So this point, I can predict it's going to be an inflection point. We'll see shortly if it is or it's not. Okay, so about intervals of increase, decrease, I would say decreasing over the interval from negative infinity all the way to 0, and then from 0 still going down, decreasing up to 3 over 2, and I would say the function is increasing over just the interval from 3 over 2 to positive infinity. It's an open interval. So intervals of increase, decrease is clear. And also the local minimum point, it was, I'm going to call it point M. It was at 3 over 2, comma. Now if you plug in the original function, you get negative 1.7 roughly. So that's the y coordinate of the minimum point. So I think we're done with these two next steps. And now we move on to concavity analysis. For concavity analysis, we have to look at the second derivative, obviously. So this time, I'm going to set the second derivative equal to 0. And I get 12x squared as the common factor. I factor it out. So I get x equals 0 or x equals 1. So I have two candidates for inflection point. We don't know if they are inflection points yet. I've mentioned this several times, that these are potential inflection points at this time. But later, we're going to figure out if the second derivative did change its sign, well, it's going to be an inflection point, certainly. If not, then not. So to do this, we are going to quickly construct another chart. This time I go 12x. These are the factors of y double prime equals 0 equation. And let's set it up quickly. Negative infinity, positive infinity. So what are we going to include here? We're going to include for sure 0 and 1. So I have 0. I'm going to have 1. And I'm going to include this one in my other chart as well. It's between 0 and 3 over 2. And you see that nothing, of course, changes there. But it doesn't make any change in the first chart because x equals 1 was not the root of y prime equals 0. And here I'm going to include 3 over 2. Okay, in this other chart, again, it's not going to make any difference because 3 over 2 is not the root of y double prime equals 0, clearly. So 12x is 0 here. It's negative to the left, positive to the right. X minus 1, 0 here. Positive, positive, negative, negative. the second derivative is 0 wherever x is 0 or x is 1. Those were the two roots of y double prime equals 0. So the product is positive, negative, positive, positive, meaning that the graph is concave up, see you tomorrow, and then concave down, compact disc, former jokes, and then we have CU, concave up, and still concave up. So we're looking at the second derivative, and we see that the graph changes its sign from, not the graph, the y double prime changes its sign from positive to negative, and it is 0 at 0. So that means that x equals 0 is actually an inflection point. And this is as per my prediction before. We see that it was an inflection point. And then at x equals 1, y double prime changes its sign from negative to positive this time. So again, we have a change in sign. So that would be, again, an inflection point, clearly. So there's two inflection points, apparently. Both of our candidates actually became inflection points. And at 3/2, nothing happens. The graph is concave up before and concave up after. It doesn't matter. So coordinates of the inflection points, now that we know that these are inflection points, why don't we announce them? So I sub 1, I sub 2, I call them, one is at 0, one is at 1. 0 is 0 was the origin, so I bet that's the first inflection point. The second one, when you plug in 1, you get 1 minus 2, which is negative 1. So that's the next inflection point. Intervals are concave up, concave down. I'm going to find it here. So concave up on the interval, let's look. It goes from negative infinity up to 0, and then it continues from 1 towards positive infinity. And the concave down on the interval from 0 to 1, obviously, and that was it. That was it. So intervals of concave up, concave down is very clear. Intervals of increasing, decreasing is also clear. Coordinates of points of inflection. So these are two points of inflection. And we have the local minimum point with no local maximum point in this case. So I'm going to put this information all together. The graph is decreasing according to the charts. So it's decreasing and it's concave up. So apparently at 0 we have an inflection point. So the graph should look like something like this. It becomes close to the origin, and then it becomes an inflection point, changes its concavity, it becomes concave down, but it is still decreasing. Watch these. These charts should talk to you over time. The function is decreasing and it's concave what? Down. So it's going to look like something like this. So that's an inflection point. We go and reach 1. Now at 1 and negative 1, we have this point here, 1 and negative 1. That's our second inflection point. Then it goes to 1.5 and negative 1.5, which is here. So it goes there. So this was an inflection point. Okay, this origin was the other inflection point. And then here we have our local minimum point, which is happening at 1.5. This is 1.5 and roughly negative 1.7. And then it goes up, it hits the x-axis at the x-intercept of 2. You see that everything we did calculate, now they become actually live. We can see it. And then after that, the graph is concave up. It continues increasing according to the first chart at the top. So it's going to go just like this towards infinity. And this is the graph of the quartic function x to the 4 minus 2x cubed that we graphed together. This is so-called point M, the minimum point. This is the first inflection point I1. This is the second inflection point I sub 2. And I think the graph is sketched properly. And we have the x-intercept. This was the x-intercept, the two of them. And I think this is complete now. So what we did, is to put everything together in step 8, and we actually sketch the curve. For any curve sketching problem, it should take about 20 minutes, roughly, plus minus 5 minutes, and you need to construct 2 charts all the time, one for y prime, one for y double prime. You need to find intervals of increase, decrease, intervals of concave up, concave down. If there are inflection points, you have to find them. Local max min, if they do exist, you have to find them. If it's a rational function, you need to find the asymptotes. Intercept analysis is very straightforward. Set x equal to 0 to find y-intercept, set y equal to 0 to find x-intercept. And domain, of course, we need to know where the function is defined. This wraps up the curve sketching section of chapter 3. And we are going to just have some sort of assessment on curve sketching part of this chapter only. The next part, which is only one section in the textbook, that's section 3.6. It's called optimization. It's a little bit harder and it's a bit different, and it's focusing on word problems. I have to give you maybe a couple of separate lectures only on the topic of optimization, and then we will have a separate quiz or something for that one single topic of optimization. And then chapter 4 and 5, I'm not worried that much. We're going to go very fast, but this unit was a bigger unit in terms of content. So remember, where there is a will, there is a way.